close your eyes for a moment. Take a deep breath. Now imagine this: every atom in your body, every particle of calcium in your bones, every molecule of iron in your blood, every breath of oxygen filling your lungs right now was forged in the heart of an ancient star that died billions of years before you were born. You are not separate from the cosmos. You are the cosmos experiencing itself. Tonight, we're going on a journey together. Not through space, exactly, though we'll travel farther than any spacecraft has ever gone. Not through time, precisely, though we'll venture back nearly 14 billion years. No, tonight, we're journeying to the very edge of understanding itself, to that first moment when everything began. This is the story of the Big Bang. But more than that, it's your story. Because understanding where the universe came from means understanding where you came from. It means grasping your place in the grand cosmic narrative that connects the first fraction of a second to this very moment. As you settle in, breathing slowly, ready to drift into dreams filled with wonder. So, get comfortable. Adjust your pillow. Let your body sink into the mattress. This journey will be gentle, soothing, yet profound. We'll explore the most spectacular event that ever occurred, and we'll do it together, at the perfect pace for your mind to absorb these cosmic truths as you gradually, peacefully drift towards sleep. Are you ready? Then let's begin at the beginning, or rather, at the moment before there was a beginning to begin with. Welcome to Sleepy Science Tales, where we explore the universe's most fascinating mysteries in the most relaxing way possible. I'm your guide on this cosmic journey, and I'm so glad you're here tonight. If this is your first time joining us, you've discovered something special. This channel exists at the intersection of curiosity and comfort, where complex scientific ideas meet the gentle art of bedtime storytelling. We believe that learning about the universe shouldn't be stressful or overwhelming. Instead, it should be exactly what it is right now: you, comfortable in bed, about to explore ideas that are simultaneously mind-expanding and deeply relaxing. Our philosophy is simple: the universe is inherently fascinating, and when presented with care, patience, and a soothing voice, scientific knowledge becomes the perfect companion for your journey into sleep. There's something almost meditative about contemplating the cosmos. The vast scales of time and space have a way of putting our daily worries into perspective, calming the restless mind and preparing us for restorative rest. Tonight's topic, the Big Bang, is perhaps the ultimate story. It's the account of everything: how time began, how space unfurled, how matter and energy came into being. It's supported by mountains of evidence, observed through the most sophisticated instruments humanity has ever created, and yet it retains an almost mythical quality, the origin story of existence itself. But don't worry if you've never studied cosmology or physics. We're not here to test you or overwhelm you with equations. We're here to wander together through ideas, to paint pictures with words to help you visualize and understand. All while your breathing slows, your muscles relax, and sleep gradually embraces you. Throughout this journey, we'll pause occasionally. We'll breathe together. We'll let ideas settle like cosmic dust, forming into understanding the way that same dust once formed into planets and, eventually, into you. So, whether you're a regular listener returning for another cosmic voyage, or a newcomer discovering us for the first time, welcome. You're exactly where you need to be. The universe waited 13.8 billion years for this moment for you to hear its origin story. Let's not keep it waiting any longer. Before we venture back to the beginning of time, just a quick, gentle reminder: if you enjoy this journey tonight, consider subscribing to Sleepy Science Tales. We publish new cosmic adventures regularly, each one designed to expand your mind while relaxing your body. And if you find this helpful for your sleep, a like or comment would mean the universe to us spun absolutely intended. It helps other curious minds find these stories. Tell us, what aspect of the universe fascinates you most? What should we explore together next? The comments section is our little community of cosmic wanderers, and we'd love to hear from you. You might also consider sharing this with someone in your life who loves to learn, who struggles to quiet their mind at night, or who simply appreciates the wonder of existence. Send them this link with a simple message. Thought you might enjoy drifting off to sleep while learning about the origin of everything. And for those of you who want to support this channel and help us create more content, there's a link to our Patreon in the description below. Our patrons get early access to episodes, bonus content, and the deep satisfaction of knowing they're helping to spread scientific wonder in the most peaceful way possible. But for now, don't think about any of that. Those buttons and links will still be there tomorrow. Right now, in this moment, your only job is to relax, to listen, to let your imagination expand while your body settles, to learn while you let go. Adjust your pillow one last time. Take a slow, deep breath in and out. Feel yourself sinking deeper into comfort. And now, let's begin. Imagine darkness. Not the darkness of a room at night, where your eyes gradually adjust and shapes emerge. Not even the darkness of a cave, deep underground, where no light has ever penetrated. No, imagine a darkness more complete than anything you've ever experienced. A darkness that exists because there is no space for light to travel through. A darkness before space itself. This is where our story begins. Though begins isn't quite the right word, because before the Big Bang, there was no before. Time itself didn't exist. Causality, the idea that one thing leads to another, had no meaning. The very framework of existence as we understand it simply wasn't there. Your mind might resist this idea. That's okay. Let that resistance go like a breath you've been holding too long. Our brains evolved to understand predators and prey, tools and shelters, social dynamics and food sources. We weren't designed to intuitively grasp concepts like the beginning of time or the origin of space. So if these ideas feel slippery, elusive, dreamlike, that's perfect. You're in exactly the right state of mind for this journey. Science is humanity's way of extending our understanding beyond what our senses and intuitions can grasp. It's our method for asking questions of the universe and actually getting reliable answers. And over the past century, through careful observation, rigorous mathematics, and brilliant insights, scientists have reconstructed the story of how everything came to be. This isn't speculation or philosophy, though it touches on both. This is based on evidence, multiple, independent lines of evidence that all point to the same extraordinary conclusion. The universe had a beginning. Not just the matter in the universe or the energy, but space and time themselves emerged from a state we can barely describe, in an event so profound that we're still uncovering its details today. As we journey through this story tonight, we'll move gently through time. We'll start with the evidence, how we know what we know. Then we'll walk through the timeline, from the first fraction of a second to the formation of stars and galaxies. We'll explore the architecture of the cosmos, the mysterious dark matter and dark energy that dominate it, and finally, we'll confront the deepest mysteries that remain. But through it all, remember, this is as much about you as it is about the cosmos, because you are made of star stuff, as Carl Sagan so beautifully put it. The story of the Big Bang is your origin story. Your autobiography begins not with your birth, not with your parents' meeting, not even with the evolution of life on Earth. It begins 13.8 billion years ago, in a flash of cosmic creation. So breathe slowly. Let your body relax completely, and prepare to witness in your mind's eye the most spectacular event ever, the moment everything began. Let's start with a question that might seem simple but isn't. How do we know the Big Bang actually happened? After all, we can't exactly rewind time and watch it occur. We can't travel back 13.8 billion years and set up cameras. No human was there to witness it. No life of any kind existed for billions of years afterward. So, how can scientists speak with such confidence about an event so distant, so extreme, so utterly beyond human experience? The answer lies in detective work on a cosmic scale. Imagine a detective arriving at a scene long after an event has occurred. The witnesses are gone, but evidence remains: fingerprints, footprints, residue, traces. A skilled detective can reconstruct what happened by piecing together these remnants. Cosmologists do something similar, but instead of examining a crime scene, they examine the entire universe. And the universe, it turns out, is covered in fingerprints from its violent birth. There are three main pillars of evidence that support the Big Bang theory. Three independent observations that all point to the same conclusion. Think of them as three witnesses who never met each other, but whose testimonies align perfectly. When independent lines of evidence converge on the same answer, scientists take notice. In the 1920s, an astronomer named Edwin Hubble, the one the telescope is named after, made a remarkable discovery. He observed that distant galaxies were moving away from us. Not just a few galaxies in one direction, but galaxies in every direction, all receding from our vantage point. Even more remarkably, he found a pattern. The farther away a galaxy was, the faster it appeared to be moving away. This relationship, now called Hubble's law, was profound. It meant the universe was expanding, with space itself stretching like the surface of an inflating balloon. Now, take a breath here. Let that image settle in your mind. Imagine dots on a balloon's surface. As the balloon inflates, every dot moves away from every other dot. Not because the dots themselves are moving across the balloon, but because the surface they're on is expanding. This is how galaxies move apart. Space itself is growing. If the universe is expanding now, that means it was smaller in the past, smaller yesterday than today, smaller 1,000,000 years ago than yesterday, smaller 1,000,000,000 years ago than 1,000,000 years ago. Follow this logic backward and you reach an inevitable conclusion. At some point, everything in the universe was compressed into an incredibly small, incredibly dense, incredibly hot state. That moment of extreme compression, that cosmic beginning, is what we call the Big Bang. The second pillar is the cosmic microwave background radiation, but we'll explore that in detail in the next chapter. For now, just know this: the universe is bathed in a faint glow of ancient light, the cold remnant of the Big Bang's intense heat, and we can detect it with radio telescopes. It's like the universe still has a fever from its birth, and we can measure it. In those first minutes after the Big Bang, the universe was a nuclear furnace. It was hot and dense enough for nuclear fusion to occur, the same process that powers stars. But this cosmic furnace only lasted a few minutes before the universe expanded and cooled below the temperature needed for fusion. During those brief minutes, hydrogen nuclei fused together, creating helium and tiny amounts of lithium and other light elements. Then the fusion stopped, freezing the elemental composition of the universe. When astronomers measure the ratio of hydrogen to helium in the oldest parts of the universe, regions that haven't been altered by star formation, they find something remarkable. About 75% hydrogen and 25% helium, with traces of lithium. This matches with stunning precision the predictions of Big Bang nuclear synthesis, the calculations of what should have formed in those first 3 minutes. This isn't just a rough match. The numbers line up to multiple decimal places. It's like finding a fragment of pottery at an archaeological site, and when you analyze it, discovering it's made from clay that could only have come from one specific river that existed thousands of years ago. The specificity of the evidence is compelling. So we have 3 independent observations. The universe is expanding. There's radiation left over from the early universe, and the abundance of elements matches what we'd expect from a hot, dense beginning. Each of these alone would be suggestive. Together, they form an overwhelming case. But science isn't about blind faith in theories. It's about making predictions and testing them. The Big Bang theory has made numerous predictions about the temperature of the background radiation, about the distribution of galaxies, about the presence of certain isotopes, and these predictions have been confirmed again and again. This is why scientists accept the Big Bang not as speculation, but as the best description we have of the universe's history. It's a framework that explains what we observe and successfully predicts what we should find. When we look deeper, as you lie here, relaxing, letting these ideas wash over you, consider this: the evidence for your own cosmic origin is literally everywhere. It's in the radio waves passing through your bedroom right now. It's in the composition of the air you're breathing. It's in the light from distant galaxies, traveling for billions of years just to reach your eyes. The universe is telling its story constantly. To anyone willing to listen, let's dive deeper into that second pillar of evidence, because it's perhaps the most direct glimpse we have of the infinite universe. the cosmic microwave background radiation, or CMB. The story of its discovery is almost as fascinating as the discovery itself. In 1964, two scientists named Arno Penzias and Robert Wilson were working with a large radio antenna at Bell Labs in New Jersey. They were trying to eliminate all sources of interference, aiming for the quietest possible readings. But no matter what they did, they detected a persistent noise, a faint hiss coming from all directions in the sky. At first, they thought it might be interference from New York City. They pointed the antenna away from urban areas. The noise remained. They thought it might be from radio broadcasts or from the Milky Way, or even, and this is true, from pigeon droppings in the antenna. They cleaned out the pigeons and their mess. The noise was still there. What they'd stumbled upon was the afterglow of creation itself. The cosmic microwave background is light electromagnetic radiation that has been traveling through space for nearly 13.8 billion years. It was released when the universe was just 380,000 years old, in an event cosmologists call recombination. Let me paint you a picture of what the early universe was like, and why this moment was so special. For the first 380,000 years after the Big Bang, the universe was opaque. It was filled with a hot, dense plasma soup of electrons and atomic nuclei, mostly hydrogen and helium. Light couldn't travel very far in this plasma because it kept bumping into free electrons. Imagine trying to see through fog so thick it's almost solid. That was the early universe, bright, hot, but opaque. But as the universe expanded, it cooled, and when it reached a temperature of about 3000 Kelvin, roughly the temperature of a red-hot piece of metal, something crucial happened. It became cool enough for electrons to combine with atomic nuclei, forming the first neutral atoms. Suddenly, light could travel freely. The fog cleared. The universe became transparent. All the light that had been trapped in that plasma was released in that moment, flooding through space in all directions. That light has been traveling ever since through the expanding universe for 13.8 billion years. But here's the beautiful part. As the universe expanded, the light stretched too. The wavelengths of that ancient light, originally in the visible spectrum, what we'd perceive as a warm, reddish glow, have been stretched by the expansion of space itself, shifting into the microwave part of the spectrum. This is called redshift, and it's a direct consequence of expansion. Imagine drawing a wave on a rubber band, then stretching the rubber band. The wave gets longer, stretched out. That's what happened to the light from the early universe. Today, that ancient light reaches us as microwaves, with a temperature of about 2.7 Kelvin, just 2.7 degrees above absolute zero. The universe has cooled dramatically from its blazing youth. And here's what's truly extraordinary. This radiation is almost perfectly uniform, no matter where we point our radio telescopes, north, south, toward the center of our galaxy or away from it. We detect this radiation with nearly the same intensity and temperature. This uniformity tells us something profound. The early universe was remarkably smooth and homogeneous. There were tiny variations, more on that in a moment, but overall, matter and energy were distributed very evenly in that infant cosmos. The discovery of the CMB was revolutionary. It confirmed a key prediction of the Big Bang theory, and effectively ended debates about whether the universe had a beginning. Since that initial discovery, satellites have mapped the CMB in extraordinary detail. Missions like COBE, WMAP, and Planck have created maps showing the tiny temperature variations across the sky. These variations are incredibly small temperature differences of just a few millionths of a degree, but they're crucial. They represent tiny density variations in the early universe, regions that were slightly more dense or slightly less dense than average. These density variations were the seeds of all structure in the universe. The slightly denser regions had slightly more gravity, pulling in more matter. Over millions of years, these tiny variations grew, eventually forming the first stars, then galaxies, then clusters of galaxies, then the vast cosmic web we see today. When scientists look at maps of the CMB, they're seeing a baby picture of the universe, a snapshot from when it was just 380,000 years old, and hidden in the pattern of tiny temperature variations. is information about what the universe is made of, how fast it's expanding, its geometry, and its ultimate fate. It's like finding an infant's photograph and being able to determine not just what they'll look like as an adult, but their entire life story, where they'll live, what career they'll have, how their relationships will unfold. That's how much information is encoded in the CMB dot as you lie here, breathing slowly, drifting peacefully. Consider this, right now, at this very moment. Ancient photons from the edge of the observable universe are passing through your body. They've been traveling for nearly the entire age of the universe, carrying information from a time before stars, before planets, before anything complex existed. You're bathed in the light of creation constantly. Without even noticing, special instruments can detect this radiation and decode its secrets. But it's always there, a whisper from the earliest moments of time, telling anyone who listens, this is how it began. This is where you come from. The cosmic microwave background is proof direct, measurable, undeniable proof that the universe had a hot, dense beginning. It's the echo of the Big Bang, reverberating through space and time, reaching across billions of years to tell us our origin story. Let that thought settle as your breathing slows. The same laws of physics that shaped the cosmos in its first moments are operating now. In this room, in your body, in every heartbeat and breath. You are connected to that ancient beginning in ways both literal and profound. Now let's explore that third pillar of evidence, the abundance of light elements in the universe, and what they tell us about those first crucial minutes after the Big Bang. This is one of the most elegant pieces of evidence for the Big Bang, because it involves prediction and observation aligning with breathtaking precision. In the late 1940s, physicists including George Gamow, Ralph Alpha, and Robert Herman performed calculations based on the Big Bang model. They asked a simple but profound question: if the universe began in an extremely hot, dense state and expanded rapidly, what would happen to matter during those first minutes? They realized that for a brief window of time starting about 1 second after the Big Bang and lasting just a few minutes, the universe would be at precisely the right temperature and density for nuclear fusion to occur. Nuclear fusion is the process that powers stars. It's what happens when atomic nuclei smash together with enough energy to overcome their electromagnetic repulsion and fuse into heavier elements. In stars, this happens deep in their cores where temperatures reach millions of degrees. But in the early universe, everywhere was this hot. The entire cosmos was a gigantic nuclear reactor. During this brief epoch, called Big Bang nucleosynthesis, hydrogen nuclei, just single protons collided and fused. First, they formed deuterium, a heavy form of hydrogen with 1 proton and 1 neutron. Then deuterium nuclei fused with more protons, forming helium-3. Those fused with neutrons to make helium-4, the common form of helium. Some small amounts of lithium-7 also formed, and trace amounts of other light isotopes. But then, just a few minutes after it started, the fusion stopped. The universe expanded and cooled below the temperature needed for fusion. The nuclear reactor turned off, freezing the composition of matter. Now here's where it gets really interesting. Gamow and his colleagues calculated, based on the Big Bang model and known nuclear physics, what the ratios of these elements should be. They predicted that when the fusion stopped, the universe should be about 75% hydrogen and 25% helium by mass, with much smaller amounts of deuterium and lithium. This wasn't a vague prediction. It was specific, quantitative, testable, and when astronomers measured the composition of the oldest stars formed from primordial gas that hasn't been enriched by previous generations of stars, they found exactly what Big Bang nucleosynthesis predicted. About 75% hydrogen, 25% helium, with traces of deuterium and lithium in the amounts predicted. The agreement is remarkable. We're talking about predictions made by calculating what should have happened in the first 3 minutes of the universe, and observations of matter billions of years later. And they match. This convergence of theory and observation is one of the great triumphs of modern cosmology. But let's dig a little deeper into why this is such compelling evidence. 1. Key point is that stars can't easily explain these ratios. Stars do create helium from hydrogen, that's what powers them. And they create heavier elements like carbon, oxygen, iron. But stars would have a hard time producing exactly 25% helium and no more. The ratio would vary from place to place depending on how many. Generations of stars had lived and died. Yet, when we observe the most pristine gas in the universe, gas in remote, dwarf galaxies that formed very few stars, or intergalactic gas clouds, we find the same helium abundance everywhere, about 25%. This uniformity suggests it wasn't made by stars, but by a universal event, the Big Bang itself. Another key point is deuterium. Deuterium is fragile. It's easily destroyed in stars. So stars destroy deuterium, they don't create it. The only known way to produce the amount of deuterium we observe is in the first few minutes of the Big Bang, when astronomers measure the deuterium abundance and compare it to predictions. They can determine something remarkable: the density of ordinary matter in the universe. The amount of deuterium that survived those first minutes depends sensitively on how dense the universe was. More density means more collisions, and less deuterium left over. By measuring deuterium abundance, we can essentially weigh the ordinary matter in the universe. And this measurement from Big Bang nuclear synthesis agrees with completely independent measurements from the cosmic microwave background and from observing galaxy clusters. 3 different methods, 3 different types of observations, 3 different areas of physics, all giving the same answer. This is how science builds confidence. As you relax here, breathing slowly, body sinking into comfort, consider the journey of a helium nucleus. It formed in the first 3 minutes after the Big Bang in the cosmic furnace. For billions of years, it drifted through space, perhaps eventually becoming part of a gas cloud, then part of a star, then through some pathway of cosmic recycling, part of you. Every breath you take contains helium atoms from balloons, yes, but also from the ancient universe. The helium in a child's birthday balloon is genuinely primordial, unchanged since the universe was 3 minutes old. The atoms in your body have different origins. The hydrogen is mostly primordial, from the Big Bang. The helium in your blood used in deep-sea diving and medical imaging is ancient beyond reckoning. But the heavier elements, the carbon in your DNA, the calcium in your bones, the iron in your blood, those were forged in stars and scattered through space when those stars died. You are made of both the oldest and newer materials in the universe, a mixture of Big Bang relics and stellar creations. Atoms with different histories, all coming together in the intricate, temporary, beautiful pattern that is you. The abundance of light elements is evidence written into the very fabric of matter. It's a signature that can't be forged, can't be explained away, can't be attributed to anything other than a hot, dense beginning. Every helium balloon, every distant gas cloud, every ancient star tells the same story. The universe began in fire, cooled rapidly, and left behind a specific elemental signature that we can read like a message from the deep past. And that message says, I had a beginning, and you, billions of years later, are part of what I became. Now that we understand the evidence, let's walk through the actual timeline of the Big Bang. We'll start at the very beginning, or rather, at the earliest moment we can meaningfully describe. The first second of the universe's existence was unlike anything that has existed since. In that single second, the universe transformed dramatically multiple times, passing through phases so extreme that matter as we know it couldn't exist. Let's begin at the Planck time, about 10 to 43 seconds after the Big Bang. That's a decimal point followed by 42 zeros, and then a 1. This is the earliest moment we can discuss with any confidence, the boundary where our current understanding of physics breaks down. Before the Planck time, quantum effects and gravity were equally important, and we don't yet have a theory of quantum gravity that can describe what happened. It's not that we know what happened and can't explain it, we literally don't know what questions to ask yet. This is the realm where physics itself becomes uncertain, where space and time as we understand them may not have existed in any conventional sense. But at the Planck time, the universe emerges into a state we can begin to describe. If barely, the temperature was unimaginably hot, about Kelvin. To put that in perspective, the core of our Sun is about 15 million Kelvin. This was billions of trillions of times hotter. At these temperatures, matter as we know it couldn't exist, even protons and neutrons. The building blocks of atomic nuclei couldn't hold together. What did exist was a seething soup of fundamental particles and forces. Energy and matter were interchangeable, constantly transforming into each other according to Einstein's famous equation, E equals mc. Particles popped into existence and annihilated back into energy. The universe a roiling quantum foam dot in this earliest fraction of a second. The four fundamental forces we know today: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were likely unified into a single force. As the universe expanded and cooled, these forces separated from each other, like water freezing into ice, each taking on distinct properties. First, gravity separated from the other forces. Then, as the universe continued to cool, the strong nuclear force separated. Finally, the electromagnetic and weak forces, briefly unified as the electroweak force, split into the two distinct forces we observe today. This all happened in less time than it takes light to cross the width of an atomic nucleus. By about 10 to 11 seconds 100 billionth of a second, the universe had cooled to a comparatively balmy Kelvin, and the four fundamental forces were now distinct. The universe was filled with a quark-gluon plasma, a soup of quarks and gluons, the fundamental constituents of matter. Quarks are the particles that combine to form protons and neutrons. Gluons are the particles that carry the strong nuclear force, binding quarks together. In this early plasma, it was too hot for quarks to bind into composite particles. They existed freely, along with electrons, neutrinos, and photons, all in thermal equilibrium. Then, at about 1 microsecond, 1/1,000,000th of a second after the Big Bang, something crucial happened. The universe cooled below Kelvin, the temperature at which quarks combined together. In an event called the quark epoch ending, quarks combined in groups of 3 to form protons and neutrons, the particles that would eventually make up atomic nuclei. This is called confinement. Quarks became confined inside composite particles. From this moment forward, the fundamental building blocks of atoms existed. By the time the universe was 1 millisecond old, 1,000th of a second, it was filled with protons, neutrons, electrons, neutrinos, and photons, all in a hot, dense plasma. The temperature was now about 10 billion Kelvin, still far hotter than the core of any star, but cool enough that these particles were stable. And then, around 1 second after the Big Bang, another critical transition occurred. The universe became cool enough that neutrinos, ghostly particles that barely interact with matter, stopped colliding frequently with other particles. They decoupled from the rest of the matter and energy, streaming freely through space. Those neutrinos are still out there, forming what's called the cosmic neutrino background. Unlike the cosmic microwave background we discussed earlier, this neutrino background hasn't been directly detected yet. Neutrinos are extremely hard to observe, but we're confident it exists. It would tell us about the universe at 1 second old, even earlier than the CMB. Take a slow, deep breath here. Let these time scales sink in, even though they're almost incomprehensible. The entire universe went from a state beyond description to a cosmos filled with the building blocks of atoms, all in 1 second. In that single second, more change than has changed in the entire 13.8 billion years since. By the end of the first second, the universe was about a few light seconds across, roughly the distance from Earth to the Moon. It was filled with protons, neutrons, electrons, and photons at a temperature of about 10 billion Kelvin, and it was ready for the next phase, the formation of the first atomic nuclei. As you lie here, consider that in the time it takes you to read this sentence, the early universe passed through transformations so profound that the laws of physics themselves were taking on their final form. The forces that govern your body, that hold atoms together, that power stars and determine the behavior of galaxies, all emerged and separated in that first second. Time itself was different then, not just faster or slower, but different in its very nature, with quantum effects playing a role in the fabric of space-time that we can barely imagine. The first second of the universe was a crucible where everything was forged, where the rules were written that would govern all that followed. After that first second of extreme transformation, the universe entered a brief but crucial phase, Big Bang nuclear synthesis. The formation of the first atomic nuclei. By now, the universe was about 1 second old. The temperature had dropped to roughly 10 billion Kelvin, still incredibly hot, but cool enough that protons and neutrons could collide without immediately being blown apart by thermal energy. But there was a problem. Neutrons are unstable. When a neutron is free, not bound inside an atomic nucleus, it decays. On average, a free neutron lasts about 15 minutes before it transforms into a proton, emitting an electron and a neutrino. So in the early universe, there was a race against time. Neutrons needed to find protons and bind with them into stable nuclei before they decayed away. The universe was cooling rapidly, expanding, and neutrons were steadily disappearing. At about 1 second after the Big Bang, the ratio of neutrons to protons was roughly 1 neutron for every 7 protons. This ratio was determined by the temperature and the rates of various particle interactions. In that first second, as the universe cooled, fewer neutrons were being created, and more were decaying into protons. By the time the universe was about 1 minute old, the temperature had dropped to about 1 billion Kelvin, still far hotter than the core of the Sun, but within the range where nuclear fusion could begin. Protons and neutrons started colliding and sticking together. First, a proton and neutron combined to form deuterium-heavy hydrogen, with 1 proton and 1 neutron. This is the crucial first step, and it couldn't happen earlier because at higher temperatures, the deuterium nuclei would be immediately blasted apart by high-energy photons. Once deuterium could survive, the nuclear cascade began rapidly. Deuterium nuclei collided with protons, forming helium-3, which has 2 protons and 1 neutron. Deuterium also collided with neutrons, forming tritium with 1 proton and 2 neutrons. Then these isotopes collided and combined, forming helium-4, the common, stable form of helium. With 2 protons and 2 neutrons, helium-4 is particularly stable, much more so than its mass would suggest. This stability is why helium-4 became so abundant. Nearly every neutron that survived to this point ended up locked inside a helium-4 nucleus. Some nuclei tried to go further, building heavier elements, but there was a problem, a gap. There are no stable nuclei with 5 or 8 nucleons, the collective term for protons and neutrons. It's called the 5-8 gap, and it's a quirk of nuclear physics. You can't easily build from helium-4 for nucleons to anything heavier because the 5-nucleon nucleus is unstable and falls apart almost immediately. In stars, this gap is eventually overcome through a slow, rare process where 3 helium-4 nuclei collide almost simultaneously, forming carbon. But in the early universe, the density was dropping too fast, and the window of opportunity was too brief. So, Big Bang nuclear synthesis essentially stopped at helium-4, with small amounts of deuterium, helium-3, and lithium-7 also forming. By about 3 minutes after the Big Bang, the temperature had dropped below 100 million Kelvin, still incredibly hot. But to cool for fusion to continue, the nuclear reaction stopped. The elemental composition of the universe was set. At this point, the universe was about 75% hydrogen and 25% helium by mass, with trace amounts of deuterium and lithium. This is the primordial composition we discussed earlier, the signature that remains in the oldest parts of the universe today. Take a moment here to appreciate the precision of this process. Those 3 minutes of nuclear synthesis determined the fuel for every star that would ever exist. The abundance of hydrogen meant stars could form and shine for billions of years. The abundance of helium affected how stars would evolve. The trace amounts of other elements provided signatures we can measure today. If the conditions had been slightly different, if the universe had been slightly denser, or slightly hotter, or if the fundamental forces had slightly different strengths, the elemental composition would be different. Stars might not form the same way. Life as we know it might not be possible. But the conditions were what they were, and the result was a universe ready to make stars. planets, and eventually you. After those first 3 minutes, the universe entered a long, relatively uneventful phase. It was still far too hot for atoms to form. That wouldn't happen for another 380,000 years. The universe was filled with a plasma of nuclei, electrons, and photons, all in thermal equilibrium. It was opaque, a glowing fog, cooling gradually as it expanded. But the drama of those first 3 minutes was over. The fundamental building blocks were in place. Protons, neutrons, and electrons existed in the right ratios. Nuclei of hydrogen and helium drifted through the plasma. All that remained was waiting for the universe to expand and cool enough for the next major transition. As you breathe slowly, deeply, let yourself feel the patience of the cosmos. After 3 minutes of furious activity, the universe settled into a long, gradual cooling. There was no rush, no deadline, just the inexorable expansion of space, the steady decrease of temperature, and a drifting of particles through the cosmic plasma. In 3 minutes, the fuel for all future stars was created. In 3 minutes, the composition of matter was determined. In 3 minutes, the universe set the stage for everything that would follow. And now, billions of years later, we can look back and reconstruct those 3 minutes with extraordinary precision. We can calculate what happened, predict what should be left over, and then observe the universe to check our predictions. And every time we check, the universe confirms the story. Yes, this is how it happened. This is how I began. The first 3 minutes were the universe's moment of creation, its period of elemental genesis. Everything that came after stars, galaxies, planets, life, consciousness, your thoughts as you drift towards sleep, all of it depended on what happened in those 3 crucial minutes. The universe made the building blocks. Time would assemble them into wonders. After those dramatic first 3 minutes, the universe entered what might seem like an anticlimax, a long period of gradual cooling and expansion with no major transitions. But this period, lasting 380,000 years, was crucial in its own way. The universe at 3 minutes old was a plasma hot soup where atomic nuclei and electrons existed separately, unable to combine into neutral atoms. Photons of light scattered constantly off the free electrons, unable to travel far. The universe glowed with brilliant light, but that light couldn't escape the fog of electrons. It was like being inside a star, bright but opaque. As the universe expanded, it cooled. The temperature dropped from billions of degrees to millions, then to hundreds of thousands. But for all those years, it remained hot enough to keep electrons from binding to nuclei. During this time, small density variations that had been imprinted even earlier, perhaps during a period called cosmic inflation, which we'll discuss later, were present in the plasma. These variations were tiny, just slight overdensities and underdensities, but they were important. In regions that were slightly denser, gravity was slightly stronger. These regions tried to collapse under their own gravity, but the pressure of the hot plasma resisted the collapse. The result was oscillations, sound waves, essentially traveling through the cosmic plasma. These acoustic oscillations, cosmic sound waves propagating through the entire universe, created a pattern of compressions and rarefactions. Where the plasma was compressed, it was hotter. Where it was rarefied, it was cooler. This pattern of temperature variations was frozen into the universe at the moment of recombination, the moment when electrons finally combined with nuclei to form neutral atoms. And this brings us to one of the most important moments in cosmic history, recombination, occurring about 380,000 years after the Big Bang. By this time, the universe had cooled to about 3000 Kelvin, roughly the temperature of a hot oven or a red-hot piece of metal. At this temperature, electrons could finally bind to nuclei without immediately being knocked free by high energy. Photons. Electrons combined with protons to form neutral hydrogen atoms. Electrons combined with helium nuclei to form neutral helium. In a relatively brief period, maybe just tens of thousands of years, the universe transitioned from a plasma of free electrons and nuclei to a gas of neutral atoms. And in that moment, the universe became transparent. The photons that had been trapped, scattering endlessly off free electrons, were suddenly free to travel unimpeded through space. Light could move in straight lines across the cosmos for the first time. All the light that had been trapped in the plasma was released in one great flood, streaming in all directions. This light has been traveling ever since for 13.8 billion years, cooling and stretching with the expansion of space. This is the cosmic microwave background we discussed earlier, the light from recombination, now redshifted from visible wavelengths to microwaves, reaching us as a faint glow from every direction in the sky. When we observe the CMB, we're seeing the universe as it was at 380,000 years old. We're seeing the pattern of hot and cold spots imprinted by those acoustic oscillations. We're seeing the seeds of all future structure galaxies, clusters, superclusters encoded in tiny temperature variations. It's the oldest light we can observe, a direct snapshot of the infant universe. But from the universe's perspective, recombination meant something else. For the first time since the Big Bang, the cosmos was neutral and transparent. If you could have been there with human eyes, though, of course you couldn't survive the temperature. You would have witnessed the greatest sunrise imaginable. Imagine, the universe had been filled with a glowing fog for 380,000 years. Then, as recombination occurred, the fog cleared. Suddenly, for the first time, you could see not far, because the universe was still relatively small and uniform, but you could see in principle. Light could travel freely. This moment also marked another transition. Before recombination, radiation photons dominated the energy density of the universe. After recombination, matter atoms became dominant. This transition from a radiation-dominated to a matter-dominated universe changed how structure formation proceeded. In a radiation-dominated universe, density perturbations couldn't grow effectively because radiation pressure resisted gravitational collapse. But in a matter-dominated universe, gravity could begin pulling matter together, amplifying those tiny initial density variations. The stage was set for structure formation, for the collapse of matter into the first stars and galaxies. But that wouldn't happen immediately. Take a deep breath here. Feel yourself sinking deeper into rest. The universe, too, was entering a period of rest, or rather, darkness. At 380,000 years old, the universe consisted of neutral hydrogen and helium gas, spread almost uniformly through expanding space. There was the faint glow of the cosmic microwave background. But as the universe continued to expand, even that light stretched and cooled, shifting into infrared and beyond. The universe grew dark. Stars had not yet formed. Galaxies did not yet exist. The universe was filled with cold, neutral gas, slowly clumping together under gravity's patient pull. Before we move to that next phase, the cosmic dark ages, let's pause to appreciate where we are in the story. In just 380,000 years, the universe went from an inconceivable quantum foam to a cooling, expanding space filled with atoms. The temperature dropped from infinite, or at least beyond our ability to describe, to 3000 Kelvin. The size grew from smaller than an atom to millions of light years across. Atoms now existed. The fundamental particles were bound into stable structures. The universe was transparent, matter-dominated, and ready to build complexity. All the pieces were in place for the next chapter, the formation of stars, galaxies, and all the wondrous structure we see in the cosmos today. As you lie here in the dark, comfortable and peaceful, reflect on this. The darkness of your room is not so different from the darkness of the early universe after recombination. A calm, neutral emptiness full of potential, waiting for light to return. After the brilliant moment of recombination, when the universe became transparent and light was released, something unexpected happened. The universe went dark. This period, from about 380,000 years to about 100 million years after the Big Bang, is called the Cosmic Dark Ages, and it's one of the least understood epochs in cosmic history. It's called the Dark Ages not because the universe was literally dark, though it was, in a sense, but because we have very little direct observational data about this period. It's a gap in our cosmic photo album, a time we can model and simulate but have not yet directly observed. Here's what we think happened after recombination. The universe was filled with neutral hydrogen and helium gas. This gas was cooling as the universe expanded. The cosmic microwave background radiation provided a faint glow, but it was quickly redshifting into infrared and radio wavelengths as space stretched. More importantly, there were no stars yet, no galaxies, no sources of visible light. The universe was genuinely dark in the way we think of darkness. No stars to look at, no galaxies to illuminate the void, just vast expanses of cold gas slowly drifting through expanding space. But even in this darkness, change was happening. Remember those tiny density variations we discussed? The ones imprinted in the cosmic microwave background? Those weren't just interesting patterns, they were the seeds of everything to come. In regions where the gas was slightly denser, gravity was slightly stronger. These denser regions pulled in more gas from their surroundings, becoming denser still. This is a runaway process. More density means more gravity, which attracts more matter. Increasing density further, slowly, over tens of millions of years, the gas began to clump. Small density variations grew into larger ones. The universe developed structure, transitioning from nearly uniform to distinctly lumpy. But this structure was forming in the dark, unseen, like a sculpture being carved in a pitch-black room. There's another crucial element to this story: dark matter. We'll explore dark matter in more detail later, but for now, understand that dark matter doesn't interact with light. It doesn't emit, absorb, or scatter photons. It's invisible to our eyes and telescopes, detectable only through its gravitational effects. And dark matter makes up about 85% of the matter in the universe. During the Dark Ages, dark matter was already clumping together under gravity. Because dark matter doesn't interact with radiation, it could begin collapsing earlier than ordinary matter, unhindered by radiation pressure. Dark matter formed the gravitational scaffolding halos and filaments that ordinary matter would eventually fall into. Think of dark matter as the invisible frame of a building, with ordinary matter as the walls and windows we can see. The frame went up first, during the Dark Ages, determining where and how ordinary matter would gather. Ordinary matter, the hydrogen and helium gas, fell into these dark matter halos. As it did, it lost energy and sank toward the centers of the halos, forming dense clouds. And in the densest parts of these clouds, something remarkable began to happen. The gas pressure and temperature started to rise. Gravity was compressing the gas, heating it through the energy of infalling material. Eventually, in the densest cores, conditions became extreme enough for nuclear fusion to ignite. The first stars were being born. This moment, the formation of the first stars, marks the end of the Dark Ages and the beginning of the cosmic dawn. Also called the Epoch of Reionization, these first stars were different from modern stars. They were made almost entirely of hydrogen and helium, with essentially no heavier elements, no carbon, no oxygen, no iron. Astronomers call these population 3 stars, and none have ever been directly observed. They formed when the universe was between 100 and 200 million years old, and they were likely massive, perhaps 100 times the mass of the Sun or more. These massive stars burned intensely hot and bright, living fast and dying young. They produced ultraviolet radiation, high-energy light capable of ionizing hydrogen, stripping electrons off atoms. As more and more of these first stars formed, their ultraviolet radiation began to ionize the hydrogen gas around them, creating bubbles of ionized gas in the neutral universe. These bubbles grew and merged as more stars formed. Over hundreds of millions of years, the universe transitioned from mostly neutral to mostly ionized again, not because it was hot, as it was before recombination, but because stellar radiation was energetic enough to ionize the gas. This is the Epoch of Reionization, and it marks the moment when the universe lit up again. The Dark Ages were ending. The cosmos was coming to life with the light of the first stars. As you lie here in darkness, eyes closed, drifting peacefully, consider the patience of the universe. After the drama of the first 3 minutes and the clearing of the fog at 380,000 years, the cosmos waited in darkness for 100 million years. 100 million years of slow change, of invisible structures forming, of matter gradually coalescing under gravity's gentle but inexorable pull. 100 million years of preparation. And then, in scattered points throughout the universe, Light returned. Not the diffuse glow of the cosmic microwave background, but point sources stars, brilliant and fierce, illuminating the darkness for the first time since recombination. Imagine being there, in that dark universe, as the first star ignited. One moment, endless darkness. The next, a point of light, solitary and bright, pushing back the void. And then another star, and another, until the universe sparkled with them. Bubbles of ionized gas growing and merging, structure becoming visible for the first time. The Dark Ages were over. The universe had lit the first candles in its long night, and everything that followed, galaxies, planets, life, consciousness, depended on this moment, when gravity and matter conspired to ignite fusion in the heart of a collapsing cloud, creating the first stars and ending the cosmic darkness. Now that we've walked through the timeline from the Big Bang to the first stars, let's zoom out and look at the bigger picture. How did the universe develop the large-scale structure we see today? When we look at the modern universe with powerful telescopes, we don't see a uniform distribution of galaxies. Instead, we see an intricate pattern: galaxies clustered together in groups and clusters. Those clusters connected by filaments of galaxies, and between these filaments, vast empty regions called voids. This is called the cosmic web, and understanding how it formed is one of the great achievements of modern cosmology. The story of structure formation begins with those tiny density variations in the early universe, the ones we discussed that were imprinted in the cosmic microwave background. These variations were incredibly small density differences of only about 1 part in 100,000, but small variations, given enough time and the amplifying power of gravity, can grow into dramatic structures. Here's the basic process. In regions that were slightly denser than average, gravity was slightly stronger. These regions attracted more matter from their surroundings. As more matter fell in, the region became denser still, and its gravity increased further. This is what scientists call gravitational instability, a runaway process, where small differences grow into large ones. Meanwhile, regions that were slightly less dense than average lost matter to the denser regions. They became even less dense, forming the voids we see today. This process happened on multiple scales simultaneously. Small-scale density variations collapsed first, forming relatively small structures. These then merged and combined, building larger structures in a hierarchical process. Think of it like water droplets on a window. Small droplets form first, then run into each other and merge into larger drops, which combine into even larger streams. Structure in the universe formed through a similar process of collapse and merger, from small to large. But there's a complication. This process worked differently for dark matter and ordinary matter. Dark matter, as we mentioned, doesn't interact with light or ordinary matter except through gravity. This means it could begin collapsing immediately after recombination, unhindered by any pressure forces. Dark matter clumped freely under gravity alone. Ordinary matter, however, interacts with radiation and as pressure. Before recombination, radiation pressure prevented ordinary matter from collapsing on small scales. Even after recombination, gas pressure resisted collapse. This meant that dark matter formed structures first, creating gravitational wells like valleys in space that ordinary matter then fell into. The dark matter provided the gravitational scaffolding for structure formation. This is why dark matter is so crucial to our understanding of structure formation. Computer simulations that include only ordinary matter fail to reproduce the universe we observe. The structures formed too slowly, and galaxies as we see them today wouldn't have had time to form. But simulations that include dark matter match observations beautifully. The dark matter collapses first, forming halos. Ordinary matter falls into these halos, cools by radiating energy, and collects in the centers, forming galaxies. Let's walk through the process in more detail. First, during and after the Dark Ages, dark matter collapsed into halos, concentrations of dark matter bound together by gravity. These halos formed a complex, web-like pattern because the initial density variations were not random, but had structure on various scales. Ordinary matter, hydrogen, and helium gas fell into these dark matter halos. As it fell, it gained speed and energy, But unlike dark matter, ordinary matter could lose this energy by colliding with other matter and radiating energy away as heat and light. This cooling process was crucial. As the gas cooled, it contracted further, concentrating in the centers of the dark matter halos. The cooling continued until densities and temperatures became high enough for stars to form. The first stars, as we discussed, were massive and short-lived. They fused hydrogen into helium, and through the process of fusion, they created the first heavy elements: carbon, oxygen, silicon, iron, and others. When these massive stars exhausted their fuel, they exploded as supernovae, scattering these newly created elements into the surrounding gas. This enriched gas could cool more efficiently than pristine hydrogen and helium, because elements like carbon and oxygen are very effective at radiating energy with better cooling. The next generation of stars could form more easily and in greater numbers, and these stars formed in increasingly large collections the first galaxies. Galaxies continued to grow through two main processes: accretion and mergers. Accretion is the process of gas falling into a galaxy from its surroundings, providing fresh material for new star formation. This was especially important in the early universe when gas was abundant. Mergers happen when two galaxies collide and combine. This sounds violent and it can trigger intense bursts of star formation. But remember that galaxies are mostly empty space. The stars themselves rarely collide. Instead, the galaxies pass through each other and gravity gradually binds them into a single, larger galaxy. Our own Milky Way galaxy formed through both processes. It accreted gas and merged with smaller galaxies throughout its history. In fact, we can still see remnants of past merger streams of stars in the Milky Way's halo that came from dwarf galaxies torn apart by our galaxy's gravity. And the Milky Way story isn't over. In about 4 billion years, we'll merge with our large neighbor, the Andromeda Galaxy, forming an even larger galaxy. Take a slow breath here. Let this cosmic story wash over you. The galaxies you see in astronomy pictures, the Milky Way you might glimpse on a dark night, these aren't static objects. They're dynamic, evolving systems, continuously shaped by gravity, constantly accreting matter and merging with neighbors. Structure formation is an ongoing process, not something that finished in the distant past. As you relax deeper into rest, consider the scales involved. The tiny variations imprinted in the cosmic microwave background were about 400,000 light-years across. Through billions of years of gravitational amplification, these grew into structures millions and billions of light-years in size. The universe took quantum fluctuations, random variations on the smallest scales, and amplified them into galactic superclusters, the largest gravitationally bound structures in the cosmos. From the smallest to the largest, from quantum uncertainty to cosmic architecture, the universe built structure through the patient, inexorable action of gravity. And that structure includes the galaxy that contains our solar system, the solar system that contains Earth, and the Earth that contains you. You are a small part of a galaxy, which is a small part of a cluster, which is a small part of the cosmic web. All of it descended from tiny ripples in the fabric of the early universe. Structure formation is how the universe organized itself, how it went from nearly uniform to richly complex, how it created the cosmic stage on which the drama of stars, planets, and life could unfold. Let's explore in more detail this cosmic web, the large-scale structure of the universe, because it's one of the most beautiful and surprising discoveries of modern astronomy. When you look at a map of galaxy distributions, and astronomers have now mapped the positions of millions of galaxies, you see a striking pattern. Galaxies aren't scattered randomly through space. Instead, they form a web-like structure of filaments, sheets, and clusters, with enormous voids in between. Picture a sponge or the foam in a bubble bath. The galaxies are like the thin surfaces of the bubbles, forming interconnected sheets and filaments, while the voids are like the empty space inside the bubbles. This is the cosmic web. The numbers are staggering. Galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity, can be millions of light-years across. The filaments connecting these clusters can stretch for hundreds of millions of light-years, And the voids, the empty regions, can be over 100 million light-years across, containing very few galaxies. To put that in perspective, our entire Milky Way galaxy is about 100,000 light-years across. The distance to the nearest large galaxy, Andromeda, is about 2.5 million light-years. These are the scales we're used to thinking about. But the cosmic web operates on scales 100 times larger. It's the architecture of the universe itself, the largest coherent structures that exist. How did this web form? The answer takes us back to the earliest moments after the Big Bang, during a period called cosmic inflation, which we'll discuss in more detail later. Quantum fluctuations were stretched to cosmic sizes. These fluctuations created density variations on a wide range of scales, from small to very large. When matter began to collapse under gravity, it didn't collapse in isolation. Different regions were connected by the overall pattern of density variations. Matter flowed along paths of least resistance, following the gravitational gradient. Imagine water flowing downhill. It doesn't flow randomly, it follows valleys and channels carved by the landscape. Similarly, matter in the early universe flowed along the gravitational landscape created by density variations. Where multiple streams of matter converged, clusters formed. The paths matter followed became filaments, and regions where density was lower than average became the voids. Evacuated as matter flowed toward denser regions. Computer simulations of this process, starting from the density variations observed in the cosmic microwave background, and applying our understanding of gravity and dark matter, produce a cosmic web remarkably similar to what we observe. This is a powerful confirmation that we understand the basic physics of structure formation. Let's explore the components of the cosmic web in more detail. Clusters are the nodes of the web, the most massive gravitationally bound structures in the universe. A typical galaxy cluster might contain hundreds or thousands of galaxies, with a total mass of 1,000,000 billion times the mass of the Sun. Most of that mass in the form of dark matter. The galaxies in clusters are moving rapidly, held in orbit by the cluster's gravity, like bees swarming around a hive. Clusters also contain vast amounts of hot gas that was heated to tens of millions of degrees as it fell into the cluster's gravitational well. This gas is so hot it emits X-rays, which we can detect with space telescopes. Our own local group containing the Milky Way, Andromeda, and about 80 smaller galaxies is a small structure by cosmic web standards. We're located at the edge of a larger structure called the Virgo supercluster, which itself is part of an even larger structure called Laniakea. Filaments are the connections between clusters, like threads in a spider web. They're elongated structures, hundreds of millions of light-years long but relatively narrow, perhaps 10 or 20 million light-years thick. Filaments contain galaxies strung out along their length. Along with dark matter and gas, matter is still flowing along filaments, feeding into the clusters at their ends. This means structure is still forming, the cosmic web is still being woven. Astronomers have been able to detect the gas in filaments, not by seeing it directly, but by observing how it absorbs light from distant quasars. As light travels from a quasar toward us, passing through filaments, the gas absorbs specific wavelengths, leaving dark lines in the quasar's spectrum. Sheets or walls are two-dimensional structures where galaxies are distributed across a surface. The most famous example is the Sloan Great Wall, a vast sheet of galaxies stretching over 1 billion light-years. These sheets often form the boundaries of voids. Voids are the empty regions, the spaces between the filaments and sheets. They're not completely empty. Few lonely galaxies drift through them, but they're remarkably underdense compared to the cosmic average. Voids formed because they were slightly less dense than average in the early universe. As denser regions pulled matter toward themselves, the voids became more empty. It's a self-reinforcing process, interestingly. Galaxies in voids are often different from galaxies in clusters. Void galaxies tend to be smaller, younger, and still actively forming stars, while cluster galaxies are often older and have stopped forming stars. This makes sense. Voids have less matter and less gravitational interaction. So, galaxies that revolve more slowly and peacefully dot as you breathe slowly. Relaxing deeper, picture this web stretching through space. Imagine zooming out from Earth, past the Moon, past the planets, out of the solar system, out of the Milky Way. You see our galaxy is one of billions, and as you continue zooming out, the web reveals its self-filaments of light connecting bright clusters, vast dark voids. An intricate pattern woven through space. The cosmic web is beautiful in its complexity. Yet it emerged from simple physical principles, gravity acting on initial density variations. Over billions of years. It's a reminder that complexity doesn't require complex rules. Simple laws, given enough time and space to operate, can create structures of breathtaking intricacy. And here's something profound to consider as you drift towards sleep. The cosmic web determines the large-scale structure of the universe, but it also influences everything within it. The Milky Way's location in the cosmic web affects how it formed, how it acquired gas to make stars, which other galaxies it encountered and merged with. These factors influenced the formation of our solar system, the conditions on Earth, and ultimately, the evolution of life. Your existence is connected to the cosmic web. If the initial density fluctuations had been different, the web would have a different pattern. The Milky Way would have formed differently, or perhaps not at all. And you wouldn't be here. The architecture of the universe on the largest scales is linked to the smallest details, including you, lying here, contemplating it all. The cosmic web is the universe's fingerprint, the unique pattern created by its history, visible to anyone who looks closely enough at the distribution of galaxies across the sky. Throughout our discussion of structure formation and the cosmic web, one element has repeatedly appeared: dark matter. It's time to address this mysterious component directly. Dark matter is one of the most profound puzzles in modern physics. We're confident it exists. Evidence for it is overwhelming and comes from multiple independent observations. Yet we don't know what it is. We've never directly detected a particle of dark matter. It's called dark not because it's black, but because it doesn't interact with light at all. It doesn't emit light, doesn't absorb light, doesn't reflect or scatter light. It's completely invisible to our eyes and to telescopes that detect electromagnetic radiation. So, how do we know it's there? Through gravity. Dark matter has mass, and mass creates gravity. We can detect dark matter by observing its gravitational effects on things we can see: stars, galaxies, light itself. Here are the key pieces of evidence. First, galaxy rotation curves. When astronomers measure how fast stars orbiting galaxies, they find something strange. Stars far from the galactic center are moving much faster than they should be based on the visible matter, according to Newton's laws. If most of a galaxy's mass is concentrated in the center in the bulge of stars, and the supermassive black hole, then stars farther out should orbit more slowly, just like outer planets in our solar system orbit more slowly than inner planets. But observations show that stars maintain high speeds even at the edges of galaxies. This suggests there's additional, unseen mass distributed throughout and around the galaxy, providing extra gravity to keep those outer stars moving fast. Second, gravitational lensing. Einstein's general relativity tells us that mass warps spacetime, and light follows the curves of spacetime. This means massive objects can bend light like a lens. When we observe distant galaxies through galaxy clusters, we often see the distant galaxies distorted and magnified, their light bent by the cluster's gravity. By measuring this distortion, we can calculate how much mass is in the cluster, and consistently, the mass needed to create the observed lensing is much greater than the mass we can see in stars. And hot gas? There must be additional, invisible mass. Dark matter. Third, the cosmic microwave background and structure formation. As we discussed, the pattern of temperature variations in the CMB contains information about the universe's composition. The specific pattern we observe the sizes and amplitudes of the hot and cold spots tells us that the universe must contain about 5 times more dark matter than ordinary matter. Additionally, computer simulations show that structures like galaxies and the cosmic web couldn't have formed in the time available unless dark matter existed to provide extra gravitational pull, allowing structures to form faster than ordinary matter alone could manage. So what is dark matter? That's the billion-dollar question literally. In terms of the research funding devoted to finding out, the leading hypothesis is that dark matter consists of particles that don't interact with electromagnetic fields. These will be particles outside the standard model of particle physics, our current theory of fundamental particles and forces. Various candidates have been proposed. WIMPs, weakly interacting massive particles, axions, sterile neutrinos. Experiments around the world are searching for these particles, trying to detect them directly or create them in particle accelerators. So far, no confirmed detection. Dark matter remains elusive, hiding in plain sight throughout the universe. But here's what we do know. Dark matter makes up about 85% of the matter in the universe. In terms of the total energy content of the universe, dark matter is about 27%. This means that the atoms, molecules, and particles we're familiar with, everything in the periodic table, everything you're made of, everything you've ever seen or touched makes up only about 5% of the universe. We are, quite literally, a minority component of the cosmos. Take a moment to absorb this. Breathe slowly. Let your body relax into this humbling reality. The universe is mostly made of something we can't see, don't understand, and can't yet detect directly. The matter we're made of, that stars and planets are made of, is almost a contaminant, a small addition to the dominant dark matter, and yet that small percentage is crucial. Ordinary matter can cool and condense, forming stars and planets. It can bond into complex molecules, creating chemistry and life. It interacts with light, allowing eyes to evolve and see the universe. Dark matter may dominate by mass, but ordinary matter brings complexity, structure, information, and consciousness. Dark matter provided the scaffolding. Ordinary matter provided the story. As you drift deeper into rest, consider that you're surrounded by dark matter right now. It passes through your body constantly, undetected and undetectable. A ghost substance that permeates everything yet touches nothing. The universe keeps its secrets well. If dark matter is mysterious, dark energy is even more so. It's the strangest component of the universe, the most recent major discovery in cosmology, and it may determine the ultimate fate of everything. The story begins in the 1990s, when two teams of astronomers were studying distant supernovae exploding stars. They were using a particular type of supernova, called Type Ia, which has a known intrinsic brightness, by measuring how bright these supernovae appear from Earth, and comparing it to their known true brightness. Astronomers can calculate how far away they are. The teams were measuring the distances to many of these supernovae across the universe, trying to determine how the expansion of the universe has changed over time. Everyone expected to find that the expansion was slowing down. After all, gravity pulls things together. If the universe contains matter, then galaxies should be gravitationally attracting each other, slowing down the expansion that began with the Big Bang. The question was how much the expansion had slowed. But when the data came in, something shocking emerged. The expansion wasn't slowing down. It was speeding up. Distant supernovae were dimmer than expected, meaning they were farther away than expected, meaning the universe had expanded more than expected. The expansion rate was accelerating. This discovery, announced in 1998, was so unexpected that the teams checked and rechecked their data, but the conclusion was inescapable. The universe's expansion is accelerating, driven by something providing a kind of repulsive gravity, pushing space apart. That something was named dark energy. Dark energy makes up about 68% of the total energy content of the universe, more than dark matter, much more than ordinary matter. It's the dominant component of the cosmos, but we have almost no idea what it is. Here's what we know. Dark energy behaves as if it's a property of space itself. As the universe expands and more space comes into existence, more dark energy appears. This is very different from matter, which becomes less dense as the universe expands. The same amount of matter spread through larger volume. Dark energy maintains constant density even as space expands, which means the total amount of dark energy increases. And this dark energy exerts negative pressure, a repulsive effect that causes space to expand faster. The simplest explanation is something called the cosmological constant. represented by the Greek letter lambda lambda. This is a term that Einstein actually introduced into his equations of general relativity, though he later removed it, calling it his greatest blunder. The cosmological constant represents the energy of empty space vacuum energy. Quantum mechanics tells us that empty space isn't truly empty. It's seething with quantum fluctuations, particles and antiparticles popping in and out of existence. This quantum activity could give space itself an energy density. If this vacuum energy is positive and evenly distributed, it would act exactly like dark energy, causing accelerated expansion. But there's a problem when physicists calculate what the vacuum energy should be based on quantum mechanics. They get a number that's vastly larger, about 10,120 times larger than what we observe. This discrepancy is called the cosmological constant problem, and it's one of the deepest unsolved problems in theoretical physics. So either our calculations are profoundly wrong, or something we don't understand is cancelling out almost all of the vacuum energy, leaving just the tiny amount we observe as dark energy. Alternative theories suggest dark energy might not be constant, but could change over time, a dynamic field rather than a property of space. This hypothetical field is sometimes called quintessence. Experiments and observations are ongoing to test whether dark energy is truly constant or evolving. Why does dark energy matter for the universe's fate? Because it determines whether the universe will expand forever or eventually recollapse. With dark energy causing accelerated expansion, the universe will continue expanding, faster and faster, forever. Galaxies will move away from each other at increasing speeds. Eventually, billions of years from now, distant galaxies will be receding so fast that their light can't reach us anymore. The observable universe will shrink even as the actual universe grows. This is very different from what would happen without dark energy. Without it, the expansion would gradually slow, perhaps eventually stopping and reversing in a big crunch, the opposite of the Big Bang. But with dark energy, the universe appears headed for a cold, lonely future endless expansion into darkness. As you relax here, breathing slowly. Let this sink in. The universe is not just a collection of matter and energy following gravity's rules. There's something else, something pervading all of space, pushing against gravity, driving galaxies apart. The universe is expanding, and that expansion is accelerating, driven by the most abundant yet least understood component of reality. Dark energy is the universe's final mystery, the deepest puzzle, the question mark hanging over cosmology. We can measure its effects, but we don't know its nature. The cosmos keeps its greatest secret in plain sight, hidden in the very fabric of space itself. Let that thought carry you deeper into rest, into the mystery of existence itself. We've traveled far together tonight, from the first fraction of a second after the Big Bang to the large-scale structure of the universe. We've discussed evidence, timelines, dark matter, and dark energy. We've painted a picture of cosmic history based on solid observations and well-tested theories. But science is not about having all the answers. It's about asking better and better questions. And cosmology, despite its tremendous successes, is filled with profound mysteries, questions we can ask but can't yet answer. Let's explore some of these mysteries as you continue to relax, to drift, to let your mind wander through the unknown. The nature of dark matter. We've discussed that dark matter exists and comprises most of the matter in the universe. We can observe its gravitational effects. We can map its distribution, but we don't know what it is. Is it a particle? If so, why hasn't it been detected despite decades of increasingly sensitive experiments? Or is it something else entirely, perhaps a modification of gravity that mimics dark matter's effects? The search continues in laboratories deep underground, shielded from cosmic rays, where scientists hope to catch a rare interaction between a dark matter particle and ordinary matter. So far, nothing confirmed. The nature of dark energy. Even more mysterious than dark matter, dark energy is the strangest component of the universe. Is it Einstein's cosmological constant, a property of space itself? Is it a dynamic field that changes over time? Or is it evidence that our theory of gravity needs modification on cosmic scales? We're in the peculiar position of knowing that dark energy makes up 68% of the universe, while having almost no idea what it actually is, the matter-antimatter asymmetry. According to our understanding of particle physics, the Big Bang should have created equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other, producing pure energy. So why does the universe contain matter but virtually no antimatter? Why didn't everything annihilate in the early universe, leaving only radiation? There must have been some asymmetry, some process that created slightly more matter than antimatter, perhaps one extra matter particle. For every billion matter-antimatter pairs, all the matter we see today, including you, came from that tiny excess. But we don't know what caused this asymmetry. It's one of the fundamental questions about why the universe has the properties it does. The horizon problem. When we observe the cosmic microwave background, we find that it is almost exactly the same temperature in all directions, about 2.7 Kelvin everywhere, with variations of only 1 part in 100,000. This uniformity is puzzling. Regions of the universe that are on opposite sides of the sky have never been in contact with each other. They're separated by more distance than light could have traveled in the age of the universe. So, how did they come to have the same temperature? When two things are at the same temperature, it's usually because they've been in thermal contact, exchanging energy until they equalize. But these regions were never in contact. So, why are they the same temperature? This is called the horizon problem, and the leading solution is cosmic inflation, a period of extremely rapid expansion. In the first fraction of a second after the Big Bang, we'll discuss inflation in the next chapter. But for now, know that it's a hypothesis, not a confirmed theory. We have suggestive evidence, but not definitive proof. The flatness problem. The universe appears to be geometrically flat. Parallel lines stay parallel. The angles of a triangle add to 180 degrees. Space behaves like the Euclidean geometry you learned in school. But general relativity allows for curved universes. Space could be positively curved, like the surface of a sphere, or negatively curved like a saddle. The fact that our universe is flat or extremely close to flat is puzzling, because a flat universe is an unstable state. Imagine balancing a pencil on its point. It's possible in principle, but the slightest perturbation will cause it to fall. Similarly, a universe that starts out slightly non-flat should become increasingly curved over time. The fact that our universe is so flat suggests something made it that way, and again, inflation is the leading hypothesis, the measurement problem of quantum mechanics. This isn't specifically a cosmology problem, but it touches on the earliest moments of the universe, when quantum effects dominated. Quantum mechanics describes particles existing in superpositions, multiple states, simultaneously until measured. But what counts as a measurement? Does consciousness play a role? And if the universe began in a quantum state, what measured it and caused it to take on definite properties? These questions touch on the foundations of quantum mechanics and connect to cosmology at the moment of the Big Bang. The singularity at t equals 0. Our equations tell us that if we extrapolate backwards to the very beginning, we reach a point of infinite density and temperature as singularity. But infinities in physics usually indicate that our theories have broken down, that we're missing something. Most physicists suspect the Big Bang wasn't truly a singularity, but something else that our current theories can't describe, perhaps a quantum gravitational state requiring a theory we don't yet have. The value of physical constants. Why does the electron have the charge it has? Why is the speed of light 299,792,458 meters per second? Why is the cosmological constant the tiny value it is? These constants appear arbitrary in our theories. We measure them experimentally, but we can't derive them from first principles. Yet, if they were even slightly different, the universe would be profoundly altered. Stars might not form, atoms might not be stable, complexity might not arise. This has led some physicists to propose the anthropic principle. We observe the constants we do, because only universes with these values can produce observers. If true, this might suggest a multiverse, many universes with different constants. and we find ourselves in one compatible with our existence. But this is speculation, venturing beyond what we can currently test. As you lie here, deeply relaxed, breathing slowly, consider how much we don't know. The universe has revealed many of its secrets, but it holds many more. Every answer raises new questions. Every mystery solved uncovers deeper mysteries. This is the beauty of science. It's never finished. There's always more to learn, always deeper to go, always another layer of reality waiting to be uncovered. The universe is not a puzzle to be solved and set aside. It's an infinite source of wonder, constantly revealing new depths the more carefully we look. And you, lying here in the darkness, contemplating these mysteries, are part of that process. Human consciousness is the universe's way of understanding itself. Your thoughts about the cosmos are the cosmos thinking about itself. The mysteries remain, inviting exploration, waiting for the next generation of scientists to probe deeper, to ask better questions, to uncover truths we can't yet imagine. For now, let these mysteries wash over you like waves, each one a reminder that existence is stranger and more wonderful than we ever imagined. Now we come to perhaps the deepest mystery of all. What happened before the Big Bang? Or, more precisely, is there even such a thing as before the Big Bang? This question takes us to the very edge of physics, to the boundary between science and philosophy, to ideas that are speculative yet fascinating. According to general relativity, space-time itself began with the Big Bang. Time is not a container that existed before the universe. Time is part of the universe. So asking what came before the Big Bang is like asking what's north of the North Pole. The question itself may not make sense. St. Augustine understood this back in the 4th century. When asked what God was doing before creating the world, he replied that there was no before because God created time along with the world. Modern cosmology has reached a similar conclusion through physics rather than theology. But human minds resist this idea. We're accustomed to causality, to the idea that every event has a prior cause. The thought that time itself began, that there was no before, feels incomplete, unsatisfying. So, physicists have explored various ideas about what might have preceded or caused the Big Bang. Cosmic inflation is the leading scientific hypothesis. According to inflation theory, the universe underwent a period of exponentially rapid expansion in the first tiny fraction of a second, starting at perhaps 1036 seconds and lasting until about 1032 seconds after the Big Bang. During this brief moment, the universe expanded by a factor of at least 1026, growing from smaller than a proton to about the size of a marble, or perhaps much larger. This inflationary period would solve several problems we mentioned earlier: the horizon problem and the flatness problem. If all the observable universe came from a tiny region that was in thermal contact before inflation, then it makes sense that it is uniform temperature, and inflation naturally drives the universe toward flatness. Like blowing up a balloon makes its surface appear flatter. Inflation also explains the origin of structure. Quantum fluctuations during inflation would be stretched to cosmic sizes, creating the density variations that eventually became galaxies and clusters. But here's the crucial point: inflation doesn't explain where the universe came from. It just pushes the question back. If the universe underwent inflation, what started inflation? What existed before inflation began? Some theorists propose that inflation may be eternal, that our Big Bang was just one bubble in an eternally inflating space, and that new bubbles, new universes are constantly forming. This is called eternal inflation, and it suggests a vast multiverse of bubble universes, each with potentially different physical laws. But this is speculation, very difficult to test observationally since we can't access other bubble universes. Quantum cosmology offers another approach. In quantum mechanics, particles can tunnel through barriers, appearing on the other side even when they don't have enough energy to go over the barrier. This is called quantum tunneling, and it happens routinely in the atomic world. Some physicists, including Stephen Hawking, have proposed that the universe itself might have tunneled into existence from nothing, or rather, from a quantum state where the distinction between space and time breaks down. In Hawking's no boundary proposal, the universe has no beginning. in time because time itself gradually emerges from a more fundamental, timeless quantum state. It's like asking when the Earth began. There's no age where the Earth starts. If you travel to the South Pole, you just smoothly curve around. Similarly, if you go back to the beginning of time, time smoothly transforms into something else, a quantum geometry where time and space are indistinguishable. This is mathematically elegant but profoundly difficult to visualize or test. Cyclic models propose that the Big Bang wasn't the beginning but just the latest in a series of cosmic cycles. Perhaps the universe expands, then contracts in a big crunch, then bounces back in a new Big Bang, over and over eternally. Some versions of string theory, a theoretical framework attempting to unify quantum mechanics and gravity, allow for such cyclic universes, but we have no observational evidence for previous cycles, and it's unclear whether information could survive a cosmic bounce from one cycle to the next. The multiverse idea comes in several forms. Eternal inflation produces a multiverse of bubble universes. Quantum mechanics might produce a multiverse through the many worlds interpretation, where every quantum event spawns new universes. String theory allows for a vast landscape of possible universes with different properties. If the multiverse is real, then our universe, with its particular properties and physical constants, is just one of countless others. The constants we measure aren't fundamental but environmental. They vary from universe to universe, and we find ourselves in one where they allow for stars, planets, and life. This would explain the seemingly fine-tuned nature of our universe. Without requiring a designer its selection bias, we can only observe a universe compatible with our existence. But many physicists are uncomfortable with the multiverse idea because it's not clear how to test it. If other universes are permanently beyond our observation, is the multiverse science or philosophy? Take a deep breath here. Let these ideas settle. Feel yourself sinking deeper into comfort, into the mysterious depths of existence itself. The question of what came before the Big Bang may not have a traditional answer. It may not have an answer at all in the way we usually think of answers. The universe might simply be a brute fact, existing without cause or explanation. Or there might be a deeper level of reality we haven't yet glimpsed. A framework where the Big Bang is just one event in a larger cosmic story. The physicist Max Tegmark has proposed an intriguing idea. Perhaps the ultimate answer is that the universe is mathematics. That mathematical structures don't just describe reality, they are reality. And the Big Bang is simply a particular mathematical structure unfolding. According to its internal logic, this is radical and speculative, but it captures something important. At the deepest level, the universe seems to be mathematical. The laws of physics are mathematical relationships. The constants are numbers. The structure of space and time obeys mathematical principles. As you drift here between waking and sleep, consider this. Perhaps we're asking the wrong question. Perhaps why is there something rather than nothing is unanswerable, not because we lack information, but because the question assumes a framework: causality, time, existence and non-existence that breaks down at the ultimate level. Perhaps the universe simply is, and that's the only answer there can be. Or perhaps, billions of years from now, our descendants, biological or artificial, will look back at our puzzlement and smile, the way we smile at ancient peoples who wondered what held up the earth. Perhaps the answer is obvious once you have the right conceptual framework, and we simply haven't reached that level of understanding yet. For now, we live in the question, in the mystery, in the awesome recognition that we exist in a universe whose origins remain, for the moment, beyond our full comprehension. And there's beauty in that, in being small enough to be humbled, yet conscious enough to ask the questions. Let that paradox cradle you as you drift deeper into rest. We've journeyed backward to the beginning of time. Now let's journey forward to the end, or rather, to the future of the universe over the next billions and trillions of years. What will happen to the cosmos? What is the ultimate fate of everything? The answer depends on dark energy, that mysterious component we discussed earlier. And based on our current understanding, the future looks cold, dark, and lonely, but also incredibly long. Let's walk through the timeline of the far future. In about 4 billion years, our sun will begin to run out of hydrogen fuel in its core. It will swell into a red giant, expanding beyond Earth's orbit, likely engulfing our planet. This is the end of Earth, though humanity, if we survive that long, will have had billions of years to find new homes among. The stars dot around the same time. The Milky Way and Andromeda galaxies will collide and merge, forming a larger elliptical galaxy sometimes called Milkomeda. Despite containing hundreds of billions of stars, the collision will be gentle. Stars are so far apart that individual stellar collisions will be rare, but the gravitational interaction will reshape both galaxies, triggering bursts of star formation and altering orbits. In about 100 trillion years, 100,000 billion years, star formation will largely cease. The universe will have used up most of its gas for making stars. The last stars will form from the last remaining clouds of hydrogen. After that, no new stars will be born. The universe will contain only the stars that already exist, gradually burning out one by one. Over trillions of years more, small red dwarf stars, the most common type, burn their fuel slowly and can shine for many trillions of years. The last red dwarfs won't burn out until about 100 trillion years from now, maybe longer. After the last star dies, the universe enters what's called the degenerate era. The only objects emitting significant light will be white dwarfs, the cooling remnants of sun-like stars, and neutron stars, the ultra-dense remnants of massive stars. These will gradually radiate away their heat over incomprehensible time scales. Brown dwarfs, objects too small to ignite normal fusion, will occasionally collide, briefly flaring into short-lived stars. This will be the only source of starlight in a universe that's grown cold and dark. Around key d years from now, that's a 1 followed by 40 zeros. Even white dwarfs will have cooled to black dwarfs, cold and dark, no longer emitting detectable radiation. The universe will be filled with these dark remnants, along with neutron stars, black holes, and planets drifting through the darkness, galaxies. Or what remains of them will be graveyards, collections of dead stars, slowly orbiting massive black holes at their centers. But things continue to change. Even at these vast time scales, protons, the building blocks of atomic nuclei, might not be stable forever. Some theories predict that protons decay with a half-life of perhaps 1,036 years or longer. If protons decay, then eventually all ordinary matter will disintegrate into subatomic particles and radiation. By key d years, if proton decay occurs, even black dwarfs and neutron stars will have dissolved into showers of particles. The universe will contain only black holes, radiation, and elementary particles. This is the black hole era, when black holes are the dominant structures in the universe. But even black holes don't last forever. Stephen Hawking discovered that black holes emit radiation now called Hawking radiation, due to quantum effects near their event horizons. This means black holes slowly lose mass and eventually evaporate. The time scale is extraordinary. A black hole with the mass of the Sun would take about 1,067 years to evaporate. A supermassive black hole, millions or billions of times more massive, would take 10,100 years or more. But eventually, given enough time, even the largest black holes will evaporate completely. By 10,106 years from now, a 1 with 106 zeros, even the most massive black holes will have evaporated. The universe will enter what's called the dark era, containing only radiation, fundamental particles, and perhaps the occasional positronium atom, an electron and positron temporarily orbiting each other before annihilating. Closing parenthesis. The universe will be cold, with a temperature approaching absolute zero. It will be dark, with no stars, no galaxies, no structures, just particles and photons spread across ever-expanding space, and it will be lonely, due to the accelerating expansion driven by dark energy. All the particles and photons will be so spread out that they essentially never interact. Each particle will be alone in a vast, ever-expanding void. This is called the heat death of the universe, not because it gets hot, but because it reaches maximum entropy, a state of ultimate disorder where no usable energy remains and no change is possible. In this far future, the universe will still exist, but nothing will happen. It will be like a still frame, unchanging for eternity. This sounds bleak, and in a sense it is. But consider the time scales we're discussing. The universe today is about 13.8 billion years old. The era of stars when the universe is bright and active and interesting will last for trillions of years, perhaps 100 trillion. We exist in the early universe, in the first tiny fraction of cosmic history, in an age of stars and light and possibility. We're living in the interesting times, and who knows? Perhaps advanced civilizations will find ways to survive far into the future, harvesting energy from black holes, creating new forms of matter, engineering processes we can't yet imagine. Perhaps intelligence itself can persist even as the universe grows cold, or perhaps new physics, not yet understood, will intervene. Dark energy might change over time, leading to different outcomes. The universe might be cyclic, rebounding into a new big bang. We might be wrong about proton decay or Hawking. Radiation, the far future is uncertain because it depends on physics at extremes we haven't yet tested. But based on what we know now, the universe appears headed for a slow fade, not a dramatic end, but a gradual cooling and expansion into eternal darkness. As you lie here, breathing slowly, deeply relaxed, let this timeline wash over you. Trillions upon trillions of years stretch ahead, time scales that make human history, all of recorded civilization, seem like a fleeting spark. And yet, here in this spark, in this brief moment of cosmic brightness, you exist. You're conscious, aware, able to contemplate the universe's beginning and end. The universe may end in darkness, but right now, right here, there is light, there is warmth, there is thought and wonder, and the extraordinary fact of existence. Savor it. This moment, this breath, this awareness, it's a gift from 13.8 billion years of cosmic evolution. Let yourself drift now, peacefully into dreams, carried by the current of time itself. Now, as you float peacefully between waking and sleep, let's bring this cosmic journey home. Let's talk about you, your connection to everything we've discussed, your place in this grand story. You are not separate from the universe we've explored tonight. You are not an observer standing outside, looking in. You are part of it, woven into its fabric, made from its substance. Let's trace your lineage back through cosmic history. The atoms in your body have different ages and origins, and each tells a story. The hydrogen in your body, about 10% of your atoms, is primordial, forged in the first 3 minutes after the Big Bang. When you drink water, some of those hydrogen atoms have been unchanged since the universe was 3 minutes old. They're 13.8 billion years old, nearly as ancient as time itself. Think about that. Ancient hydrogen from the cosmic dawn, flowing through your veins, part of every molecule of water, every strand of DNA, every protein. The heavier elements, carbon, oxygen, nitrogen, phosphorus, sulfur, the elements essential for life, were created in stars. Let me explain how. Stars are nuclear furnaces. In their cores, they fuse hydrogen into helium, releasing energy that makes them shine. When a star exhausts its hydrogen, it begins fusing helium into carbon and oxygen. Massive stars go further, fusing elements all the way up to iron. But fusion stops at iron because fusing iron requires energy rather than releasing it. So stars can't produce elements heavier than iron through normal fusion. Elements heavier than iron, like iodine in your thyroid. Gold in any jewelry you wear, are created in supernova explosions when massive stars die. The extreme temperatures and pressures in these explosions allow the rapid capture of neutrons, building heavier and heavier elements in seconds. When the supernova explodes, it scatters these newly created elements across space. They mix with interstellar gas clouds, enriching them with heavy elements. And from these enriched gas clouds, new generations of stars form, stars like our Sun, accompanied by planets made from the recycled material of dead stars. Every atom of carbon in your body was once inside a star, fused from lighter elements, then blown into space when that star died. The carbon in your DNA, in the proteins that form your muscles. In the carbon dioxide you exhale, all of it is stardust, billions of years old. The oxygen you breathe was forged in stellar cores and scattered by supernovae. The calcium in your bones came from stars. The iron in your blood was created in a supernova explosion. You are literally made of star material. This isn't poetry or metaphor. It's scientific fact, verifiable and true. But your connection goes deeper still. The very existence of complex atoms depends on the Big Bang. The ratio of hydrogen to helium, determined in those first 3 minutes, set the stage for star formation. Too much helium and stars would burn too quickly. Too little and stellar evolution would be different. The density variations in the early universe, imprinted in the cosmic microwave background, determined where galaxies would form. The Milky Way exists because of a slightly overdense region in the primordial plasma. Dark matter provided the gravitational scaffolding that allowed the Milky Way to form in the first place. Without dark matter, galaxies wouldn't have assembled quickly enough, stars wouldn't have formed in the same way, and you wouldn't exist. The cosmic web, the large-scale structure of the universe, influenced which galaxies merged with ours, what gas was available for star formation, and ultimately the conditions in the spiral arm of the Milky Way where our Sun formed for 0.6 billion years ago. Your existence depends on the Big Bang's properties, on the values of physical constants, on the formation of structure, on generations of stars living and dying. You are not an accident or an afterthought. You are a product of cosmic evolution, as natural and inevitable as galaxies and stars, given enough time and the right conditions. The physicist Carl Sagan said it beautifully. We are a way for the cosmos to know itself. For 13.8 billion years, the universe evolved unconsciously, stars burning, galaxies forming, chemistry happening without awareness, without reflection. Then, on at least one planet orbiting an ordinary star in an ordinary galaxy, complexity reached a threshold. Life emerged. Nervous systems evolved. Consciousness arose. And through consciousness, the universe became aware of itself. Through your eyes, the cosmos sees itself. Through your thoughts, it contemplates its own existence. You are stardust that has become conscious. Atoms organized in a way that allows reflection and wonder. The universe has created, in you, a way to experience its own grandeur. As you drift here, deeply relaxed, consider your cosmic genealogy. 13.8 billion years ago, the Big Bang occurs. A fraction of a second later, the fundamental forces separate. At 3 minutes, your hydrogen atoms are forged. At 380,000 years, the universe becomes transparent, releasing the light we see as the cosmic microwave background. Over hundreds of millions of years, the first stars form and die, creating and scattering the heavy elements. Galaxies assemble from dark matter and gas. The Milky Way takes shape. About 4.6 billion years ago, in one spiral arm, a cloud of gas and dust enriched with elements from previous generations of stars begins to collapse. The Sun ignites at its center. Surrounding it, leftover material coalesces into planets. The third planet from the Sun has the right temperature for liquid water. Life emerges on Earth about 3.8 billion years ago. Single-celled organisms evolve into complex life. Nervous systems develop. Consciousness appears. Humans evolve, acquiring the ability to ask questions about their origins. And now you lie here, breathing slowly, contemplating the journey that led to this moment. From the Big Bang to you is an unbroken chain, a continuous path of cosmic evolution. The same laws of physics that govern the early universe are operating in your body right now. The atoms that formed in stellar cores are part of your structure. The patterns imprinted in the cosmic microwave background influenced the formation of your galaxy. You are a child of the cosmos, intimately connected to its history, a temporary arrangement of ancient atoms, conscious and wondering, able to trace your lineage back to the origin of everything. And that makes you extraordinary, even as it makes you humble. Let this knowledge settle into your bones, themselves made of calcium from long-dead stars. Let it flow through your blood, carrying iron forged in supernova fires. Let it fill your breath, oxygen created in stellar cores. You are the universe, experiencing itself, if only for a brief, precious moment. As you float now in that peaceful space between waking and sleep, you might wonder, why does any of this matter? Why should we care about events 13.8 billion years ago, or about the far future trillions of years hence? Let me offer some thoughts as you drift deeper into rest. First, perspective. Understanding the cosmic scale, the vast ages, the enormous distances, the incredible complexity puts our daily concerns in context. The meeting you're worried about, the argument you had, the disappointment or frustration, these are real and valid, but they're also temporary, small against the backdrop of cosmic time. This isn't to diminish your experiences or feelings. It's to offer perspective, a wider view. You are part of something much larger than your immediate circumstances. Your struggles and joys are real, but they're also fleeting moments in a much longer story. This perspective can be oddly comforting. The universe has been unfolding for nearly 14 billion years. Stars have been born and died. Galaxies have formed and merged. And through it all, the cosmos has continued, patient and ongoing. Your troubles, too, will pass. Your challenges are temporary. The vast cosmic patience can inform your own resilience. Second, connection. Modern life can feel isolating. We're separated from nature, from community, sometimes from meaning. But the story of the Big Bang connects you to everything. You're made of the same atoms as distant stars. The same forces that shaped galaxies operate in your body. You share a common origin with every living thing on Earth, with every planet and star, with the entire cosmos. This is literal connection, not metaphorical. You are not alone or isolated. You are part of an interconnected whole, woven into the fabric of existence itself. When you look up at the night sky, you're not seeing distant, alien objects. You're seeing family, distant cousins perhaps, but family nonetheless. Every star is made of the same elements that make you. Every galaxy follows the same physical laws that govern your body. Third, humility and wonder. The universe is vastly larger, older, and more complex than human civilization. The timescales dwarf human history. The distances mock our brief journeys. The physical scales from the Planck length to the cosmic web span a range our minds can barely grasp. This should inspire humility. We are small, temporary, fragile. Our knowledge is incomplete, our understanding limited. We've existed for a blink of cosmic time, and we may disappear just as quickly. But with that humility comes wonder. Despite being small, we can understand. Despite being temporary, we can discover truths that are eternal. Despite being limited, we can comprehend the origin and fate of everything. That we can trace cosmic history from the Big Bang to the present. That we can predict the universe's far future. That we can detect the cosmic microwave background and decode its message. This is extraordinary. Consciousness is the universe's gift to itself, a way for blind matter following physical laws to become aware, to see, to know, to wonder. You, lying here, contemplating the Big Bang, are participating in one of the universe's greatest achievements, self-awareness. Fourth, meaning. Some people fear that the scientific understanding of the universe removes meaning or purpose. If we're just atoms following physical laws, does anything really matter? But meaning isn't something the universe provides, it's something we create. And understanding our cosmic context can inform the meaning we choose to create. We exist for a brief moment in cosmic history in an age of stars and light. We're conscious, capable of love and art and discovery. We can reduce suffering, create beauty, expand knowledge and wonder at existence. Isn't that meaningful? Isn't that purposeful? The universe didn't create us for a purpose. We create purpose through our choices and actions. And understanding that we're made of stardust, that we're the universe aware of itself, that our existence depends on billions of years of cosmic evolution, this can inform the purposes we choose. We might choose to honor our cosmic heritage by exploring, discovering, protecting our planet, expanding into space, ensuring that consciousness and intelligence persist. Or we might choose purposes closer to home, love, connection, creativity, joy, reducing suffering in our immediate sphere. The point is that purpose isn't given from outside, it grows from within. And understanding our cosmic context enriches the purposes we can choose. Fifth, hope. The universe's story is one of increasing complexity. From the uniform plasma of the early universe, structure emerged. From simple atoms, complex molecules formed. From chemistry, life arose. From life, consciousness appeared. The universe trends toward complexity, at least locally and temporarily. This is a source of hope. We face challenges: climate change, inequality, conflict, the existential risks of powerful technologies. But we're part of a universe that creates complexity from simplicity, order from chaos, consciousness from unconscious matter. The same process that created stars from primordial gas and life from chemistry can inspire us to believe that we can solve our problems, create better systems, evolve toward wisdom. The universe is on our side in a sense, not consciously, but through its fundamental tendency to generate complexity and organization given the right conditions. Finally, gratitude. Against all odds, you exist. The chances were vanishingly small. The right physical constants, the right initial conditions, the right sequence of cosmic events, the right stellar generations, the right planet, the right evolutionary path, the right meeting of your parents. At every step, things could have gone differently, and you wouldn't be here. But here you are, conscious and aware, able to trace your origins back to the beginning of time, able to contemplate the universe that created you. This is worthy of gratitude, not to a deity necessarily, but simply gratitude for the fact of existence, for the gift of awareness, for the opportunity to experience this strange, beautiful, mysterious cosmos. As you sink deeper into sleep now, let gratitude fill you. Gratitude for existence, for consciousness, for this moment, for the 13.8 billion years of cosmic history that led to you. You are the universe's gift to itself. You are stardust contemplating stars. You are a brief, bright moment of awareness in the vast cosmic story. And that is enough. That is more than enough. That is everything. And now our journey together comes to its natural end. We've traveled from the first fraction of a second after the Big Bang to the far future trillions of years hence. We've explored evidence and timelines, structure and mystery, the nature of reality and your place within it. Your breathing has slowed. Your body has relaxed completely, sinking into the mattress, heavy and comfortable. Your mind has wandered through billions of years and across billions of light years, and now it's ready to rest. This is the perfect state for sleep: body relaxed, mind gently tired from contemplation, thoughts drifting like stars across the darkness behind your closed eyes. As you transition into sleep, let the images from tonight float through your awareness. The cosmic microwave background, that faint glow from the infant universe, the first stars igniting in the darkness, the cosmic web stretching across space, dark matter's invisible scaffolding, dark energy's mysterious push. These images are dreamlike, aren't they? Vast and strange, beautiful and mysterious. Let them blend into your dreams, informing your rest with cosmic wonder. You are part of this story. Every atom in your body connects you to these events. You're made of star stuff, as we've discussed, literally composed of matter forged in stellar cores and scattered across space. As you drift into sleep, imagine yourself expanding, dissolving into the cosmos, your boundaries softening, your sense of separation fading. You're not just in the universe, you are the universe, temporarily organized into the pattern called you, conscious for a brief moment before returning to the great cosmic cycle. This isn't death, we're contemplating its connection, unity, the deep truth that there are no true boundaries, just continuous fields of matter and energy, organized in different ways. You are a wave in the ocean of existence, distinct for a moment, but never separate from the whole. Let this thought comfort you as you fall asleep. You're safe, held by the same forces that hold planets in orbit and galaxies in their dance. Gravity, the weakest force, but the one that shapes the cosmos, is gently holding you to Earth right now, keeping you secure. The electromagnetic force, binding atoms into molecules, is maintaining the structure of your body, the integrity of your cells, the precise chemical reactions that sustain your life even as you sleep. The nuclear forces, strong and weak, are operating in every atom, keeping your very matter stable, preventing you from flying apart. You are held, supported, sustained by the fundamental forces of nature, the same forces that shaped the universe from its beginning. There's nothing to worry about, nothing to figure out, nothing to do. The universe has been unfolding for 13.8 billion years without your effort, and it will continue just fine while you sleep. Your only task now is to rest, to release conscious control, to let your body repair and your mind process the day's experiences. Dreams may come, perhaps dreams of stars and galaxies, of cosmic webs and ancient light. or perhaps simple dreams, ordinary and personal. Whatever comes, let it come. Don't try to control or direct your dreams. Simply allow, accept, rest. The rhythm of your breathing is like the rhythm of the cosmos expansion and contraction, out-breath and in-breath, like the universe itself, which may ultimately breathe in cycles we can barely imagine. Breathe slowly, deeply, naturally. Each breath connects you to the atmosphere, which connects you to the planet, which connects you to the solar system, which connects you to the galaxy, which connects you to the universe. Each breath is cosmic. You're inhaling oxygen created in stars, exhaling carbon dioxide that will be absorbed by plants, which will release oxygen again. In the great cycle of chemistry that sustains life, you are part of these cycles: breath, water, carbon, nutrients all flowing through you, connecting you to everything. As you fall asleep now, let yourself dissolve into these connections. You're not falling into unconsciousness, you're expanding into the universe, releasing the tight focus of waking consciousness and opening into something broader, deeper, more fundamental. Sleep is a return to the cosmic state, where boundaries dissolve and only existence remains. Let yourself go now. Let sleep embrace you. Let the universe cradle you as it has for your entire life, as it always will. You're safe. You're connected. You're home. Sleep well, cosmic traveler. Sleep well. Before you drift completely away, just a few soft words about continuing this journey. If you've enjoyed this exploration of the Big Bang, this gentle journey through cosmic history, consider subscribing to Sleepy Science Tales. We're here every week with new topics: black holes, quantum mechanics, the search for extraterrestrial life, the nature of time, the evolution of Earth, the mysteries of consciousness. Each episode is designed like this one: educational but relaxing, informative but soothing, expanding your mind while calming your body. Science doesn't have to be stressful or intimidating. When presented with care and patience, when woven into bedtime stories, when paired with gentle guidance towards sleep, scientific knowledge becomes a source of comfort and wonder. Subscribe so you don't miss future episodes. Turn on notifications if you'd like to be reminded when new cosmic adventures are available. And if this helped you sleep, please leave a like. That simple click helps other people find this content, helps the channel grow, helps us continue creating these journeys. It takes a second, but it makes a meaningful difference. Comments are also wonderful. Tell us, what did you find most fascinating about the Big Bang? What questions do you still have? What topics would you like us to explore next? Our community of cosmic sleepers is kind and curious, and we'd love to hear from you. For those interested in supporting the channel more directly, we have a Patreon linked in the description. Patrons get early access to episodes, bonus content, extended versions, and the knowledge that they're making these productions possible. Even $1 or $2 per month helps us invest in better audio equipment, research time, and the resources needed to create high-quality content. But those are all tomorrow concerns. Right now, you're drifting into sleep, and that's perfect. This episode will be here whenever you need it. If you wake in the night and need help falling back asleep, you can return to any point in this journey. The cosmic microwave background will still be there, that ancient light still traveling through space. The stars will still be forming and dying. The universe will still be expanding. These truths are patient, eternal, waiting for you whenever you need them. And if you'd like to explore more tonight, we have many other episodes: shorter journeys through quantum physics, longer explorations of Earth's geological history, focused meditations on specific topics like black holes or the origin of life. All of them are designed with the same philosophy. Learning and relaxation go beautifully together. Wonder and rest are perfect companions. You can expand your understanding while releasing tension, grow your knowledge while falling asleep. Science is humanity's way of understanding the universe, and bedtime is the perfect moment to absorb that understanding when the mind is open and relaxed, when information can settle deeply, integrating into your worldview without resistance. Thank you for joining this journey. Thank you for your curiosity. Thank you for seeking knowledge even as you seek rest. The universe is grateful for your attention, as are we. Now sleep, dear cosmic wanderer. Sleep deeply and well, breathing slowly, deeply. naturally. Nothing to do, nowhere to go. Just this moment, just this breath. The universe is breathing with you, expanding with each in-breath, contracting with each out-breath. The cosmic rhythm flowing through you. 13.8 billion years have brought you to this moment, this peaceful moment, this safe, comfortable, restful moment. You are stardust, ancient and new, temporary and eternal, individual and universal. Let these paradoxes dissolve in sleep. No need to understand, only to be, only to rest. Your body knows how to sleep. It's done it thousands of times. You don't need to try. Simply allow. Thoughts may drift past like clouds. Let them. They'll pass. Everything passes. Thoughts, days, eons, all passing. What remains is awareness, consciousness, the universe knowing itself through you. And now, even that can fade, softening into sleep, gentle and natural. The cosmic microwave background bathes you in ancient light. So faint, so old, so peaceful. The stars are shining, though you can't see them now. They'll be there tomorrow. Patient as starlight, constant as gravity. Nothing requires your attention. Nothing needs your effort. The universe unfolds without you, and that's perfect. That's restful. You can let go completely. Fall into sleep like falling through space. Weightless, effortless, peaceful. The Big Bang happened once, 13.8 billion years ago, and its echoes still ripple through everything. Through space, through time, through you. You are those echoes, those ripples, that ancient event still unfolding, still expanding, still creating, still wondering. And now rest, just rest, breathing, being, sleeping, safe in the cosmos, held by the universe, drifting through the darkness between stars, peaceful, calm, deeply, deeply asleep.